Again, thanks for the ones who visited during office hours, since I just see a lot of problems you all may have. So I can help more people. 2.9?
Second one.
Tutorial or homework?
Homework.
Okay, cool. That's the one I did it already for 5 times this morning. So you may have a different eye. I saw someone having 90 amps, 65 amps. I'm having 70 amps for this current source. So the system is giving you some random numbers for some of the values. All right. So first step, because you know the current source are given, so let's just directly use the current source. Like I've been repeating myself regarding a concept for ideal sources. If it tells you it's 25 amps, you just have to trust it, right? I've been saying this for so many times. You just have to trust it. Doesn't matter whatever you have in the circuit. You have a voltage source, you have a dependent current source, whatever, doesn't matter. If it tells you it's 70 amps, it's going to be 70 amps. Just trust it. 70 amps, 70 amps. All right? 25 amps, trust it, trust it. 25 amps. Because this is pointing up, we don't have to, find a current direction pointing down. It's just totally unnecessary. Let's just directly use the current direction pointing up, which is fine. Just assuming it's pointing up. I'm pretty sure if you select a direction pointing down, eventually you are getting a negative current, which is okay. So let's just assume it's going up, because the current source is already pointing up. Let's just assume it's going up. So you got 2 currents going in and 1 current going out, right? So let's assume this is I delta. What is I delta? That would be 70 amps minus 25 amps, which is 45 amps. 45 amps, right? Okay. So this is calculated. I delta is 45 amps. And because we know this is a dependent source, the current of this dependent source is 5 V delta. And V delta is the voltage label in the circuit, which is the voltage across this current source. Okay? So we know that I delta is 5 V delta. This is given because it's how this is labeled. And which is 45 amps, is already calculated. So we can calculate V delta, which is 9 volts. So we're getting 9 volts here. Is that correct? It's 9 volts here. It's the same metal. 9 volts. 9 volts. And you are thinking, hey, you got another voltage source. Is this voltage source and the current source going to affect the voltage across these 2 terminals? It may, but eventually you are getting 9 volts. That's already the final results. It's all the combination of all the sources, a voltage source and current source, is already giving that result. You just have to use it. After you know the voltage across it is 9 volts, you just directly use it. Forget about whatever inside, okay? You know the terminals, plus minus is 9 volts. And again, definitely you can ground this point, assume this is 0 volts. Like I said last time, you can assume this guy to be 2 volts, 3 volts, 1,000 volts, 10,000 volts, doesn't matter. The result is, if you assume this guy to be 10,000 volts, what is the voltage here will be? 10,009 volts. It's just the voltage difference. That's everything you care about. Like what I said in the very first week, right? If I'm grabbing two nodes, which each one has 20,000 volts over there, if I can make it at the same time, exactly, I will be fine, because even though it's 20,000 volts, but I don't have any, there's isn't any like voltage drop across me, so there's no current, so I'll be safe, right? Just relative, doesn't matter. You got 0 volts. If you have 0 volts here, and this must be 9 volts. There's another thing a student asked about in the morning, which is something I want to bring up because I know a lot of you guys may have the same question, right? R1, R2. So if the voltage is labeled as 5 volts, for example, so what is this circuit telling you? So can I say, let me just say some sentences or statements. You let me know if they are valid or not. R1's voltage is 5 volts. R1's voltage is 5 volts.
Cross it.
R1, let's say the first one, is the first one correct or not? Valid or not? What is R1's voltage? R1 is a resistor. It has 2 terminals. What does that mean? It's not specific enough. You are not. So first, this statement is wrong. It's not valid at all. You cannot say R resistor's voltage, right? You cannot say that. But can I say this is node A, for example? Node A's voltage is 5 volts. Correct. Why? Because here's 0 volts. All right. 1K ohms for each. The voltage across R1 is 2.5 volts. The voltage across R1, or the voltage dropped through R1 or across R1, is 2.5 volts. Yes. Because R1 has 2 terminals. You cannot just say like R1's voltage is something. Okay? The voltage at node B is 2.5 volts. You got 2 equivalent resistors. It's going to divide the voltage by 2 equivalent values, which is 2.5 for each. How to calculate it? You can use, you can calculate the overall current, which is I equals 5 volts over 2K. It's giving you 2.5 milliamps. Okay? So it's 2.5 milliamps, 2.5 milliamps through every single resistor. So if you know the voltage, like I said, for the Ohm's law, right? So what is Ohm's law? You got a current flows through a resistor, you got a voltage drop. So now we have a current going through that resistor. It's going to generate a voltage drop across it, which is VR2 is what? 1K ohm times 2.5 milliamps, which is 2.5 volts. So I know the voltage across it is 2.5 volts. So why I can directly say the voltage at B is 2.5 volts? Because all voltages are relative, right? What's actually happening is I run the current through R2, so it causes a voltage drop across it, which is 2.5 volts. So actually, the voltage drop across R2 is 2.5 volts. So why I can also say the voltage at this point, so VB is 2.5 volts. I can, this is also valid. Why I could do that?
So it has a positive potential compared to, I guess, node C if it was in the bottom corner.
Yeah, because here's ground, 0 volts. 2.5 minus 0 is still 2.5 volts. That's why node voltages are valid voltages, because you're comparing that voltage to ground, which is that voltage minus 0, right? It's still that voltage. So I can either say VA is 5 volts, VB, the node is 2.5 volts, or I can say the voltage across R1 is 2.5 volts, the voltage across R2 is 2.5 volts. But I cannot say the voltage, R1's voltage is 2.5 volts. It's not making any sense. Okay, now let's come back to this problem. So we got V delta is 9 volts. If I ground this point, I can directly say the voltage here is 9 volts. Right? The voltage here is 9 volts. If the voltage here is not 9 volts anymore, it's 10 volts. What's the voltage here? 19 volts. Does that make sense? So now let's just make it simple. Ground, 9 volts. So I can directly point to a node and say the voltage at that node is something. Instead of always doing 2 nodes subtraction, I don't have to do that always because I know here's 0. So 9 volts here, 9 volts here is the same metal. It's an ideal conductor. Conducts voltage without any loss because there's no components in between, so no drop. No components, no drop. Same voltage. Ideal metal conducts voltage potentials. 9 volts, 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 9 volts. All right, 9 volts. 9 volts. Because here's 9 volts, and this chemical reaction in the battery is going to force the voltage from here to be decreased by 50 volts. So if it's 9 volts here compared to ground, so what's the voltage here compared to ground? It's going to be negative 41. Because 9 volts decreased by 50 volts by whatever chemical reaction, it's going to force it. It's going to force it to decrease by 50 volts. So it's going to be 9 minus 50 will be negative 41 volts. Now you have 2 voltages across this current source, and which is plus, which is minus. Apparently, here's plus, here's minus. 0 is higher than negative 41. So it's plus minus, and because this guy is flowing out from the anode, so it's flowing out from the anode. So this guy is actually developing power. It's supplying, developing, because it has current flowing out from anode. It's supplying, it's developing, supplying. So this is one of the source, one of the components supplying. So you got a P def for this guy. What about this one? What about this source? Is this developing or supplying? So keep in mind, developing, supplying is the same, right? Absorbing, dissipating is the same terms. Yeah, this is absorbing because 70 amps is flowing into the anode. This is absorbing. What's the voltage here? 9 volts. Is that 9 volts? What's the voltage here? 0 volts. So 0 volts will be decreased by 20 volts by this chemical reaction with the battery. So you are getting negative 20 volts compared to ground at this point. So what's the voltage here? 9 volts. What's the voltage here? Negative 20 volts. What's the voltage across it? Plus 29 volts, plus minus from top to bottom, right? That clear? Any questions by far?
So you found that the delta is 9 volts, and then you assume that's the voltage going leftward. But why didn't you use 50 volts and assume that's the voltage going rightward?
You mean 9 volts what?
So you have 9 volts, then you assume every terminal going left is 9 volts. But why didn't you use 50 volts in every terminal going left?
Oh, because this is not ground. This guy is just the voltage across these 2 terminals. It's not these 2 terminals. That's the definition. So the battery only defines the voltage drop from anode to cathode, but not anywhere else. Right? You have one component is boosting the voltage for a little bit. How much is being boosted? 41 volts. Right? So that's why I got 50 volts boosted by negative 41 volts. You are getting 9 volts totally. So here is 9 volts, negative 20 volts, plus minus 29 volts. So it's plus minus and it's also supplying. So we got another component supplying. And this is absorbing, so it's not considered. What about this? 9 volts, 25 amps, also supplying, right? So just add all these three powers together to get the total developed power of the circuit. Right? Questions? Anything unclear? Just ask. Can we go to the next? I have more questions. What's up?
So this question specifically is asking us to figure out how much total power is developed in the circuit. How do we then relate all of these voltage drops to the power related in the circuit?
Because all the calculation I just ran already find out the voltage differences between the two terminals of every single component. So if you know the voltage differences, and I believe these are all positive voltages, you can calculate it eventually. You can find out they are all positive voltages. So these are the real voltage drops. And you also know the real physical current flowing, in which direction. Then you just, like what we did in the past, right? You had a black box, doesn't matter what component it is. You got a plus minus, and you have the current flowing out will be developing, flowing in will be absorbing. So if it's flowing in, you don't calculate it. If it's flowing out, you use the voltage times the current to get the P developed for that component. Then you add this, and this.
Okay. And we only care about ones that are developing current and not those that are absorbing it.
Exactly. Yeah, if it's going inside, it's absorbing. So it's another question. If they ask you to calculate the total absorbed power, then you just care about this and this. But because the power should be balanced, if you calculated these and these three power getting together, the summation, the absolute value should be the same as absorb the power of these two components. Why it's balanced? It's just one circuit. It's not supplying to anywhere else. So whatever being developed will be absorbed by other components. I mean, I would just remember it. Don't want to dig too deep into it. Like why physically, down to the atom level. Tell me. You know, just remember it's going to be balanced, right? So if you calculated the developed power will be the same as absorbed power for the absolute values, right? Can I go to the next? Okay.
Guess that was the next one.
Yeah, cool. VS is 120 volts. Can we ground it? Just ground it. Yeah, nothing's gonna go wrong. You'll find out. Just always ground the cathode. It's okay. Easier for calculations. They should actually do it for the problems. You know, but they just didn't, which is wrong. It's called asking you to calculate VO here. Yeah, definitely you can, because VO, you know the current, you know the voltage. Definitely. So, like I said, if it tells you the current is 2.5 milliamps, you just have to trust it, right? It's gonna be 2.5 milliamps that way, right? Like a one node. What's the voltage here? You see, if I ground it, I can confidently say that. What's the voltage here, right? Without making any errors, since I ground it. So what's the voltage here?
Would it
Less than 120.
You see, it's already labeled as V naught, right? It's already labeled as that. So the voltage from here to here is V naught, okay? And this is ground, right? So what's the voltage here? Yeah. So we got a what's the voltage here? 120. What is 5k ohms? What is the voltage of this resistor?
120 minus V naught.
Hey. What's the voltage of this resistor?
Doesn't have one.
It's not valid. It's not a valid statement, like I said. It has two terminals. You can say, what's the voltage drop across it, right? Or you can point to a certain node, what's the voltage here, what's the voltage, but you cannot say what's the voltage of the resistor. Doesn't make sense. Okay? What's the voltage here? 120. What's the voltage here? V out. What's the voltage across it? Well, what's the voltage drop across it? Like if I label like this, plus minus, it's 120 minus V naught, right? And over 5k ohms will be the current, according to Ohm's law. That's the current. I1, for example. And we label the current of this branch as I2, for example. Can we? You can also label it, you can also let the current going up, no problem. Okay, but let's just draw it downwards because V out is plus minus. It's probably easier. It's the same polarity as the voltage. Easier, okay? So 120 minus V out will be the voltage drop, divided by 5k will be the current, which is I1. So 1 going in, 2 going out. So I1 equals what? This plus this, right? So what is this? V naught over 2k, right? What is this? 2.5 milli. So just the one variable, you can easily calculate it. If you know V naught, you know everything in the circuit. It's already solved. Because this circuit doesn't have any other unknown nodes. If you look at it, you know this. This is ground. And this is 120. And this is V naught. You just calculate it. And this is also V naught. This is also ground. You know everything. So the circuit is solved. No unknown parameters. Everything is solved. Right? Because if you want to calculate the current, you use V naught divided by 2k. And this voltage is already calculated. And you can calculate the current here by Ohm's law as well. It's, you know everything about it. Any questions for this circuit? No? Clear? All right. How many nodes are unknown? It's just one. What's the voltage here? What's the voltage of this resistor? Another invalid statement. What's the voltage here if I ground it? V naught. That's the voltage across the resistor, but also the voltage across the two terminals, right? So this is ground, this must be V naught. What is X? 434 minus V naught over 6 ohms. Current. and I got a current 3Ix flowing into it from right to left, and another current flowing out. So Ix plus 3Ix equals V naught over 2 ohms, current flowing down. How many variables, how many equations? Can we solve everything now? No. 2 variables, 1 equation. Impossible. What's another one? So how do you find out all the equations? It could be challenging for beginners, right? I think I had the same problem when I was in undergraduate. It's look at the textbook. They have all the equations listed, but how do you know which equation you want to list? That's a problem, right? If you know the equations, just calculate it easily. But how do you know which one you want to use? You just have to find out the components that carries that variable you want to calculate. So now you have V out, V naught is ready, putting here, Ix putting here, but you probably are missing another thing with either V naught or Ix or both. So you just have to look at here, right? At Ix as V naught. You don't want to look at here, right? It's nothing. Why do you have to look at it? Look at here. So what is it? 434 minus V naught over 6 ohms, which is Ix. So 2 equations, 2 variables, you can calculate Ix and V naught.
Do you not add the 2 ohms as well for, no, never mind, I say what it, never mind.
Any question for this problem? No? Let's do tutorial 3. There's something that you need to know. Resistors in series, you know you have to add them together, right? So R1, R2, R3. So the overall resistance, like R equivalent, is R1 plus R2 plus R3. However, you have a resistor in parallel. R1, R2, R3. So I have to use KCL to find out. So you have an overall, like I total, before you getting this current split into 3 branches. So one quick question: if I drew it that way, is this equivalent as 1 pipe and split into 3 branches, and then merge to another node? Resistors, are they the same? Yes. Just being drawn in a different way. So the metal, all the metal pieces are ideal metal. You can draw in like wires like this. If you melt it, like metal can be melted, right? You melt it and it will join to one node. It's gonna be the same circuit, right? They can shrink to one node. Just a metal piece. So 1 main branch and 3 split into 3 equivalent. Doesn't matter. Not necessary to be equivalent, but 3 branch currents and merged over here and come back to the source. So voltages, we got a voltage, ground here. So that's a voltage, right? Same voltage, same metal, same voltage everywhere for the parallel branches. Okay? And if I treat this guy as a black box, and it is a R equivalent as an overall resistor, like a big resistor inside. Okay? So V over R equivalent is what? Is I total, right? Do you agree with that? Here's the V, total V. That's the total big R equivalent of the box, black box. V over R will be the total current flowing into the black box. Right? This equals what? Every single branch current. So it's a V over R1 plus V over R2 plus V over R3. So canceled. So R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So that's how you get it, how you get this equation for parallel resistors. Another thing that is super useful is called voltage dividers. Voltage dividers. Voltage dividers. Got two resistors. For example, this is the input voltage, this is output voltage. V out, R1, R2. It's ground. So V out equals V in times R2 over R1 plus R2. It's called the voltage divider theory. So why this is valid? Because it's V out over V in, and V out is the voltage across R2. It's just the one branch, so one current, right? So V out over V in, if we write this on the left-hand side of the equation, V out is I times R2, because that's the voltage across it, right? And V in is the overall voltage. It's basically the voltage across these two resistors added together. That's the overall voltage, same voltage difference from the two terminals of these series resistors. So the voltage here of these two terminals, which is V in, equals I times R1 plus R2. Right? So what is getting canceled? I is getting canceled, right? So V out over V in becomes V out over V in equals R2 over R1 plus R2. So if you move V in on the other side, you're getting V out equals V in times R2 over R1 plus R2. Super useful voltage divider equation because they share the same current. You can cancel out that current as a step.
If you actually were to use one of those, you have to connect the other end back up to the ground wire, right?
Which one connect to ground? Here?
V out. Yeah, you
Oh,
have
here?
to loop V out back around to the negative side of V, right?
That's just the output voltage.
But through some sort of circuit to be able to use the lower voltage.
So usually, for example, this voltage is being used for something, right?
Yes.
You can connect anything here.
You could, and then that thing is probably gonna act as a resistor. And won't that change the V out as well?
It's gonna change it, yes. Yes, that will change. But now we are talking about it's unloaded V out. So you don't have any load, it's just the voltage here. If you put another thing here, definitely it's gonna change it. That's why you need the buffers. You know, you can use op-amps to build buffers to increase the impedance into it, because these are not directly connected to each other, and this has a super high resistance, and the voltage is being delivered to VL, so you can comfortably drive any following circuits. So you can use buffers to figure that out in the future. Yeah, so just connect here to here, right? We'll learn this probably starting from the 5th week. Op-amps, operational amplifiers. So amplifiers, you can build buffers, you can build instrumentation amplifiers, differential amplifiers, adders, subtractors, filters, a lot of things. Yeah, we'll talk about it.
Why did you make Vn R1 plus R2?
Because Vin is I times R1 plus R2, because this is the voltage across these two resistors. And you got one I here, so one I flows through the two resistors in series. That will be I times R1 plus R2 will be the voltage of these two nodes. And it's the same voltage as the Vin.
So then why would Vout just be R2?
Why VL is not VR2? VL is the voltage across VR2. Because we did it. See? Vout is
Well,
I.
I'm just saying, like, why wouldn't it have R1 as well then?
R1 is what?
Why would it not be R1 plus R2
R1 plus R2 for what?
for Vout?
For VL. Because it's not. Since we have a ground pin here, not here. So ground is here, so here's 0 volts, right? And if we label this point as Vout, which is labeled it, you can call it whatever. Can be V minus, whatever. Just V, right? Vout. So the voltage across the resistor R2 will be the voltage from here to here, right? And here's 0 volts. That's why the voltage across R2 will be Vout. And you are thinking why the voltage across R1 is not Vout, right? Because ground is here, not here. If ground is here, what's going to happen? That's a good question, actually. What's going to happen? What's going to happen?
So we only have the top ground now.
Yeah, both.
It's gonna gain and then immediately lose its voltage over the.
So if I label this as a ground, how many grounds do you have in the circuit? 1. I label as a triangle, even though I didn't physically short it, but in the circuits, you should assume they are shorted. So what's really happening here is you shorted the battery, 2 terminals of the battery, so the current is going to flow crazily like this way and not going to anywhere else. It's getting shorted. So we're getting nothing. However, but Bradley was trying to ask another question. So let's get rid of this ground, okay? Just one ground. So it's not shorting the power, so it's still a valid circuit. If I ground here, what's going to happen? VL is what?
I times R2, R1.
Very close. It's negative I times R1. Why? Because I is flowing that way, right? So VL should be the drop from right to left. So it's going to be minus I times, because we labeled I clockwise, right? So it's going to be negative I times R1 will be VL. Is that confusing? Is it confusing for everyone? Ignore the power source for now. Ignore the power source for now. If I ground this power anode, so I grounded cathode, right? I ground cathode. Why can I ground anode? I'm just supplying a negative voltage. It's okay. I ground anode. What's the voltage here? Is it still V in?
Isn't it negative Vn?
It's not negative V in. I ground it. I told you I ground it. What's the voltage here? 0. What's the voltage here?
Negative Vn.
Yes. Okay. So 0 volts. If I'm talking about the voltage at this point, what will be the voltage compared to where? Compared to where? I'm pointing to a node, right? Voltage here, voltage there. I'm comparing to where? Ground. Where's ground? Here. Yeah. So that's VL. Where's the current flowing? I, right? From left to right. If I label that as I, so the current flowing that way will be negative I. Right? Ohm's law. Current flows through a resistor, get a voltage drop. What is the drop? What's the drop in this case? From right to left. Current flows through the resistor from right to left. What's the drop? V out. Yes. So now V out is the voltage across R1. What's the V out across R2? Is it, yeah, so what's the voltage across R2? Is it V out, still V out or no?
VM.
No, it's not V in. What's the voltage across R2?
Yeah.
Say it again?
Is it negative 20 minus V out?
Oh, we don't have numbers here. We don't have numbers.
Oh, sorry.
Yeah, so we know here's V out, right? And we know here's ground. And we know here's what?
Negative V in.
Negative V in. So what's the voltage across R2 in this case?
Negative V in minus V out.
So we are talking about probably from here to here.
V out minus V in.
Oh, no. V out minus negative V in, right? Very close. So the voltage from here to here will be V out minus V in. Still confusing? You'll get there. Trust me. Any other questions? A lot of questions, right? Okay. Right. Just asking you the equivalent resistance. Equivalent resistance. So you're looking from here, right? Looking from here. Equivalent resistance. So these are in series, right? And then parallel, okay? So you are getting what? What's the equivalent resistor of these two, of these components? You're looking from here. That's R2 in parallel with R3 plus R4, right? That's the overall resistance here. That's in parallel, in parallel. How to calculate parallel resistors? Here. Okay? So this is this box, and this box, if you plug it back into the circuit, you're getting, that's the box. Come back, R1, R5, our box, and that's our box. So what's the overall resistor from these two terminals? Yeah, so R equivalent will be R1 plus R box plus R5, right? Any questions on this? Just series parallel resistors? Okay. What about this? Any other questions for the homework due today or due anytime sooner? No? No more? I think, what's that?
How do you know that the equivalent resistance equation works?
Because I just derived it. Oh, you mean this one?
Yeah.
Yeah. See? Voltage here is the same voltage here, here, right? So voltage over the equivalent resistance, which is a box here, just you can treat it as just one resistor. So V over that big one fat resistor, and you're getting a current. And that current is the main current of the pipe. So like this is the main current of the pipe. It's getting split into 3 branches and eventually will come back here. So that's why this current equals the voltage divided by this resistor, the first branch current, the second branch current, the third branch current. So eventually these branch currents added together will merge back, will be the same main branch current.
Okay, yeah.
Yeah. And V got cancelled. And then you just move this one to the other side of the equation, right? Okay, let's see this one. What's the equivalent resistance? Headache, right? What's the equivalent resistance from these 2 nodes? There's a guy sitting here and looking across these 2 nodes. I want to figure out what's the equivalent resistance. R1, R2, R3, R5, R4, R6, R7, R8. How do you transform it into the way that I can understand easily? It just assumes there's a water flowing out from one node, starting from one of the nodes, 2 nodes, doesn't matter which one you're gonna start with. Just start, I mean, if you, let's don't ground it. So you're flowing out a current, just testing the current, it's gonna split, right? So it's like you start from node A, okay? Start splitting, right? Splitting. First is R1, and the second is R2. Split, right? Split. Split. R1, R2. So R1 goes back in series with RA. And then 2 resistors in parallel, you can calculate it, which is another resistor, goes back to B. So this resistor is R6 in parallel with R7, right? Then R2, you got this R2 split into 2 branches. So that's 2 parallel resistors. Merge it into one, so it's R3 in parallel with R5, and then this come back to B. But in between this and B, you got R4 there. Okay, that's the first step you can get, and definitely changes further. So this becomes what? One big resistor. AB, and you'll have this one is R1 plus R8 plus R6 in parallel with R7. That's the one big resistor, and then you got 3 resistors. It's just another resistor in parallel actually. So this resistor is R2 plus R4 plus R3 in parallel with R5. That's it. That's the equivalent resistor network. I think in parallel these 2, so it becomes this, just one resistor, which is R1 plus R8 plus R6 in parallel with R7, and in parallel with R2 plus R4 plus R3 in parallel with R5. Any questions on this? It's recorded. I'll submit the notes to the website today. So, okay, see you next week.
Good break.
Thanks. You too.